Hi, this is Probability and Statistics. It's 2016. I'm going to be talking about moment generating functions, and I'm not really going to talk about them generally. I'm just going to do a couple of examples. I'm just going to write down the definition. The moment generating function of a random variable is the expected value of e to the t times the random variable. And so the moment generating function is a function of t, and it's the moment generating function of the random variable y is the expected value of e to the power of ty. It's a function of t, and it has the very useful properties that if you differentiate it enough times, and sub in t equals 0, you will get the expected value of y to the whatever. Pretty sure. Yes. Just sticking that up in the notes. I do know that the expected value is yeah. So just note the kth derivative of the moment generating function evaluated at the point 0 is the expected value of y to the power of k. So in particular, m of 0 is always 1, because it's the expected value of just 1. M dashed of 0 is the expected value of y. And m double dashed of 0 is the expected value of y squared. And from the expected value of y squared and the expected value of y, you can figure out the variance. It would be the expected value of y squared minus the square of the expected value of y. Okay. So this applies whether it's a discrete distribution or a continuous distribution, and with discrete distributions you'll have to use a sum, and for continuous distributions you have to use an integral to do your expected value. But it's the same expected value that we're trying to achieve. So find the moment generating function of y, which is distributed as a binomial distribution with n and p. I don't know if your lecturer calls it bin or just b, but you know, this is clear enough. Okay. Well, the moment generating function will be the expected value of e to the ty. So what that means is that we'll get e to the ty for all of the possible values of y, and we'll multiply it by the probability distribution function, which is that for a binomial distribution, and we'll add them up. So the options for a binomial distribution go up from 0 to n. They're the numbers that y can actually be. If I was doing a Poisson distribution, it would go from 0 to infinity, because every number is a possible number for a Poisson distribution. If I was doing a Bernoulli distribution, it would go from 0 to 1, and it would have its own probability. So just worth pointing that out. So that's the standard way of doing expected values of things. And the key thing to remember when you're doing this is that t counts as a constant in this setting. Okay, t, we're saying that for various values of t, we're multiplying t by y and figuring out what this expected value is. So t counts as a constant in this setting, it's just an unknown constant. Okay, so somehow I have to figure out what this is. one of the classic tricks with anything to do with that involves a distribution function is to find the sum of the entire distribution function, because you know that that is 1. And so I need to make this look as much as possible like the distribution function of a binomial usually, because it's got an n choose y, right? So I do have something with two things to the power of y. I've got an e to the ty and a p to the y. So I might bring those together inside that power. So just to make it obvious what I'm about to do to the person reading it without watching it, I'm going to bring these things together. And I'm going to notice that e to the ty is the same as e to the t to the y. And so now if I bring them together, it's not infinity. I've been doing Maths 1b recently and they do infinite sums. That's a little disappointing, because if this was a binomial distribution, I really would need this and this to be the same. Okay. But the thing is that that binomial distribution came about. The choosers don't necessarily have to go with a binomial distribution. It could go with another theorem about how numbers work. So one of the things with discrete distributions with the sums is that you may be looking for a distribution function. You may also just happen to know what a sum comes out to. So if I happen to find the sum of, say, x to the n, I would know that would be 1 minus x to the n minus 1 over 1 minus x. So this one, I know that if I expanded out a times b to the power of, a plus b to the power of n, I would get this. I'm just going to do a little aside. A plus b to the power of n is a to the n plus n choose 1, a to the n minus 1, b plus n choose 2, a to the n minus 2, b squared, etc., all the way up to b to the n, which is y equals 0 to the n, a to the y, b to the n minus y, n choose y. So this thing here, this is just a number thing. That's not a probability thing, it's just a thing that's true about numbers. This thing here is the same as that. So when I compare this, my a in this formula is e to the tp, and my b in this formula is 1 minus p. And so now I can write that. So my moment generating function is actually e to the tp plus 1 minus p to the n, using that formula. Brilliant, and that's my moment generating function. So just to check it, I'm just going to check to see if it comes out to the correct answer for my various numbers it should. So just to check, m of 0 is e to the 0 p plus 1 minus p to the n, and e to the 0 is 1, so p plus 1 minus p is 1, which is 1, correct, that's what it should be. If you sub in 0, it should always come out to 1. M dash t will be, because of the chain rule, and then I'll have to, because of the chain rule, I'll have to multiply by the derivative of this. The p is a constant now with respect to this derivative, and that will be the same. And so if I do m dash 0, I'll get n of e to the 0 p 1 minus p n minus 1 times p e to the 0, and that is 1 and that is 1, and we get np correct. That's what the expected value should be. So I'm just checking that it works the way it should, because then at the very least I know that it's doing the right thing for the m0 and m dash to 0. Sweet. Nice. Well, while I'm at it, maybe I will do another discrete one. Just give me a moment. It won't feel like a moment to you because I'm going to pause the recording. Look, it turns out that I was looking for specific examples and I couldn't find the one I was looking for, so I'm just going to skip that. Just suffice it to say it's worth noting a couple of useful sums. Actually, just let me pop that on the next page. So some useful sums are the one that we just did. And choose y, a to the y, b to the n minus y is a plus b to the n. That's a useful sum. This may come up, I'm not sure. Y equals 0 to the n of y to the n is 1 minus y to the n plus 1 over 1 minus y. Works just as well if you put the y's the other way around. Because there will just be timing the top and the bottom by minus 1. And another good infinite sum is just this. And finally, another useful infinite sum that you would like, that the people who taught you Maths 1B would like you to remember, and does come up at least once. Sorry, this is a y, not an n. Crap. Something to the y is... Right. The sum of something to the y when y goes from 0 to n is that. Sorry about that. And the sum of something to the y as y goes from 0 to infinity, as y goes from 0 to infinity is this. And the sum of something to the y factorial is e to the something. It takes a bit of getting used to calling it y, because y is normally an outcome, and it is in that sense in statistics. It's called a y because it is an outcome, because it's a random variable. But in this case, it's the index of this sum. So these are some useful sums. And that a could be anything. It could be e to the something, it could be some thing. As long as it doesn't involve y, then this will work. Cool, there's some useful sums. Right, so let me do an example of moment generating function for a continuous distribution. Of y, which is a normal distribution, a standard normal. Okay, well, the moment generating function will be the expected value of e to the ty, which again will be e to the ty times the correct probability distribution function, which is 1 over root 2 pi e to the minus y squared on 2. If there had been a mu, there would have been a y minus mu inside that square. If there had been a sigma, there would have been a sigma squared there and a sigma squared under that square root sign as well. And we're going to have to integrate that across all of the possible values of y, which for a normal distribution is everything. And you're going, but Dave, I don't want to do the integral from minus infinity to infinity. And you go, well, that's okay, because as long as I notice an integral that I know what the answer is to, then I'll be fine. Alright, so integrals I might know the answer to is, for example, just the integral of like e to the... Like, I can do some integrals, some of them I can just do. Having a y squared up the top there does stuff us around a little bit. And there are other integrals I know. I do know that the integral of any probability density function is 1. So if I can rearrange it to get the integral of a probability density function, then that will be 1 and I'll be laughing. And so the best probability density function to go for here would be the normal distribution, because this looks very like the normal distribution already. And to make it look even more like a normal distribution, the best thing would be to multiply these two e's together. Well, that's supposed to be a little y, by the way. So when you multiply e to the power of something together, the powers will add or subtract if they're negative. And this is pretty good. Now, if this was something squared on 2, minus something squared on 2, then if this would be the probability density function of normal with the mean of whatever and a standard deviation of still 1. So really I want to try and rewrite this as something squared. So I need to complete the square. So I'll take the 2 out, the half, the minus a half out. Like that. So take a minus a half out of this, I'm left with a 1. Take a minus a half out of this, I'm left with a minus 2. And my goal is to complete the square. So this is going to be something plus something squared minus something squared. And these 3 bits together will combine together to make that squared bit there. And when you complete the square, this thing will be half the coefficient there. So the coefficient of y there is minus 2t, so the coefficient here is t. And so I'll add t squared and subtract t squared up here, so that I haven't actually done anything. The y squared minus 2ty plus t squared becomes this, and that t squared is still there. And so I get minus a half of y minus t squared plus a half of t squared. So when I sub that back in, my moment generating function becomes, so it was this, and now it's this. And I've got a bit here involving y, and that's if it was just this, I'd be good, because that would be the probability density function of normal with mean t, because I've taken off the t. So I'm going to need to remove this somehow, but it's good, it doesn't have a y in it, so I can separate those exponentials again. And because this t doesn't involve a y, because this t here, this e to the half of t squared doesn't involve a y, it counts as a constant with respect to this integral, so I can bring it out the front. And now this bit here is the sum of the probability density, the integral of the probability density function of a normal distribution with mean t and standard deviation 1. And so I've got e to the minus a half of t squared times 1, since it's the integral of the PDF of a normal distribution with mean t and standard deviation 1.
Was that not you added an extra sign to the line?
Oh, yes, you're right. I did add an extra negative sign accidentally there. So used to putting a minus there because when I do the normal distribution there is one. And so therefore my moment generating function is e to the half of t squared. Okay, nice. Well, that's lovely. And I think that'll do. There are some theorems, I think, about how moment generating functions interact with each other, but I don't even know if they're in your course, so I'm just going to leave it at that, and this is probably enough.